So all of you can see my screen. So here, so we have discussed the Bernoulli's theorem and few more concepts we will discuss. This particular problem we have discussed, and then we have discussed the restrictions or the constraint of the Bernoulli equations. Now note down this particular problem. Okay, try to solve this problem. This particular problem. What's the answer for this particular question? So here one tank is there, a large tank is there, where it is containing some immiscible inviscid fluid as shown in the figure. Three fluids are given of respective height h1, h2 and h3. They are asking what is the instantaneous discharge velocity here. So we can apply the Bernoulli equation here. Upper surface, the top surface will be the free surface. Let me consider this to be 0.1, and what we can consider. Now see, whenever you are applying the Bernoulli equation between the 2 points, those 2 points must have in the fluids which are of the same density. But here when you consider between 1 and 2, if you just apply the between 1 and 2 where P atm pressure is there, you will not be able to get the answer accurately, right? Because density at point number 1 and density in the fluids 3 is not going to be same, right? Here it is different. So what we will consider, we will consider the 2 points which are on the same density. Point number 1, point number 2, both the points are in the same liquid density 3, rho 3. So what we will do, apply Bernoulli equation between 1 and 2. This is 1 dash. Now 1 and 2. So P1 by rho g, rho 3g, because 1 point and 2 point, both the points, my dear friend, are in the liquid number 3. Liquid number 3. Now coming to the next one, V1 square divided by 2g plus the reference height. Let me consider this is as a reference, and the height will be same, that is 0 here. P2 by rho g plus V2 square divided by 2g plus Z2. Again, that is also 0 because both the points are on the same reference line. P1, what is the pressure P1 at point number 1 by the hydrostatic law? So P1 will be, we can write rho 1 GH1 plus rho 2 GH2 plus rho 3 GH3 plus P atm, whatever it is there that we are writing. For example, same thing I'm writing in this equation like this here, rho 1 GH1, rho 2 GH2, rho 3 GH3 divided by rho 3 into G. V1 square divided by 2G. V1 square, V1, what is the velocity V1? V1 will be 0. What about velocity V2? That we need to find, right? That we need to find. So that is equal to P2 is what? P atm. This is P atm divided by rho 3 into G plus V2 square divided by 2G. So when you just find the values, this P atm by rho 3G, P atm by rho 3G will cancel out. So here V2 you will be getting the answer as 2G by rho 3 and rho 3 g h1 plus rho 2 g h2 plus rho 3 g h3. So what I'm just doing, I'm just keeping this rho 3 inside the bracket term like this. So when you just compare this equation with this A option, when you take h3 as constant and when you just divide by rho 3 in all the segments, this will be completely cancel out, right? This will be completely cancel out. Just wait. Here 2g is there, right? And we have here g. So this will and this g will cancel out, right? No, just wait. Yeah, correct. And when you take g and s3 as constant, like when you take outside of the bracket, you can write further. You can further write here. Rho 1 by rho 3 h1 by s3 plus rho 2 by rho 3 h2 by h3 plus 1, like this. So this is what you have the answer. You have to keep both the points in the same fluid. You cannot apply Bernoulli equation between 1 dash and 2 because here density is what? Density at point number 1, density is what? Rho 1. At point number 2, density is what? Rho 3. And according to Bernoulli equation, 2 points, whenever you are applying the Bernoulli equation, we have to assume incompressible fluid. But here density got changed. You can try yourself. If you're not agree with this statement, apply Bernoulli equation between v1 dash, point 1 dash and 2. When you just apply the Bernoulli equation, you will end up getting this maybe B option, that is incorrect. Correct option is what? A. Once it is done, let me know. Done. Can I move to the next one? Is it done? Done. Okay, guys, note down the next concept. Pitot tube. Now, pitot tube here, very first of all, it measures what is stagnation pressure, right? But what is the principle behind this pitot tube? That is what we have to understand. Pitot tube is also working one of the example of Bernoulli equations, right? The fundamental process or maybe fundamental principle which is going behind this pitot tube is what? Bernoulli equation. That is why, when you see that in the flow which is happening like this, suppose for example, when the flow is happening in a pipe, right? Whenever the flow is happening in a particular pipe, and you will have the boundary layer formations like this, for example, from both the ends, you can consider like a two plate system. So fluid flowing in a pipe, you can consider two parallel plates consideration where both the sides from both the plates there is some boundary layer formations, right? When they merge at the center line, then only we will be having what? Fully developed flow regions. Means here, my different, what you are observing that in the central core region, you don't have any boundary layer. You have the boundary layer like this, right? So when we see, and one more assumption of the Bernoulli equation is that we cannot apply the Bernoulli equation in the boundary layer. Like that means whenever we want to place the pitot tube, we have to place at the central core region like this. That is what the reason whenever you see pitot tube, it is always being placed at the center line of the pipe, right? Because Bernoulli is applied outside the boundary layer, right? You never see Bernoulli pitot tube has been placed like this inside the boundary layer, because the fundamental principle behind this pitot tube is Bernoulli. Now that is the first thing. Second thing, a pitot tube is a small tube, right, with its open end aligned to the flow direction, and other ends is open to what? Atmosphere. It alone cannot measure the pressure or velocity of the fluid. We have to insert piezometer also. As you can see, we have to insert piezometer also. We have to insert piezometer, right? This piezometer will help us to get the values of what? P static pressure, P static. That rho gh, that rho gh we can able to get by this piezometer. Now what we will be getting out of this pitot tube? Let us consider. As the fluid is flowing in a particular pipe, right, this is a stagnation point, where very narrow region where it is fluid velocity almost becomes zero, right, in an isentropic manner, right? So there, whatever the pressure or kinetic energy of the fluid will be there, that will be converted to dynamic pressure, and that's why you will see more height than what? This piezometer in terms of what? Dynamic pressure. This dynamic pressure, when you calculate it, it will give directly the reading of what? Velocity value, right? Now, so what we will do, we will apply the Bernoulli equation between 2 points, where we will apply the Bernoulli equation between 1 and 2. 1, let me consider point number 1 here, just outside of the pitot tube, and point number 2 just inside of that pitot tube, right? So what we will be taking, point number 2 is at rest conditions. That means velocity at point number 2 will be 0, and we are applying the Bernoulli equation between 1 and 2. So we can apply the Bernoulli equation. There is no problem in that. So what is that? P1 by rho g plus V1 square by 2g plus Z1, P2 by rho g plus Z2. V2 is 0. Z1, Z2, that is being cancelled out. Both are on the same horizontal line. Both the points are on the same horizontal line, right? What about P1? P1, what is the value of P1? So here we can measure the piezometer height. Let's say from here to here, the height is, for example, h. So what we can write, my dear friend? We can write rho into g into h divided by rho g. Velocity V1, velocity of the pipe, or velocity of the fluid which is flowing in a pipe, right? So velocity of the fluid, we can write V1 v square by 2g. P2 is what? What is the value of the P2? See, let me consider this height to be y, and already we have the height h like this. Again, the fluid is coming to the rest condition. Fluid is flowing in a what? In a rest condition, my friend. Now tell me, can we apply the fluid static condition once again over here? Yes, we can apply. So what we can write? P2 rho g into h plus y. Rho g into h plus y. That is the total pressure value at point number 2, right? So rho g into h plus y divided by rho g plus 0. So when you calculate from here, V2 you will be getting under root of 2gy, or this is what the velocity of the fluid. Sorry, this is what V1, right? This is V1 we have. V1 will be equal to under root of 2gy, or we call velocity of the fluid which is flowing in a particular pipe, right? So make a note of it. Y is a dynamic head, dynamic pressure head. So there are many ways to calculate the velocity of a fluid in a pipe. That is the one way which I am showing you right now. Pitot tube is a small tube with its open end aligned to the flow directions so as to sense the full impact pressure of the fluid, and it measures the stagnation pressure, right? Whenever you will not be having any piezometer, you will not be able to measure the velocity of the fluid because okay guys, so all of you can hear me. So we have started our discussion on Pitot tube, but we couldn't do that for the past 24 hours due to some issue which happened with Wi-Fi. Now, so we have seen some basic fundamental of pitot tube, that it has been placed exactly at the centroid, means central of the pipeline, and we are measuring only with the help of pitot tube only stagnation pressure. We cannot measure the any static pressure. And whenever we want to measure static pressure, we have to insert what, piezometer or manometer. Now here there is no need of placing the manometer over here to simply measure the static pressure. So here what we are doing here, we are just placing the piezometer along with the pitot tube, and we have calculated the velocity of the fluid as under root of 2gy. Whatever the excess deflection will be there in the tube, that we can see, and that will be what, putting together in the y value, right? Now, but generally, some of you might be thinking, sir, directly we can able to see from our own eyes that whatever the height it has been raised, directly we can see. Then why the need of piezometer? No, you will see directly the total height which has been raised from here to here. You will be able to see this height. Now, how to subtract this particular height? When you place the piezometer, in the piezometer you can able to see that reading, the height reading, whatever the liquid which has been raised in the piezometer, that we will subtract with this total pressure, right? So what actually we are doing here, we are writing total pressure as stagnation pressure, right? So here whatever the Bernoulli principle we have applied, P1 square, P1 by rho g plus V1 square plus Z1, P2 by rho g plus V2 square by 2g plus Z2. So Z1, Z2, that is already being cancelled out. And here, my dear friend, this P1 by rho g, this is a static pressure. Yes or no, guys? The pressure which is measured by the piezometer, that is a stagnation pressure. Can we write that? Or simply we can write V1, what we can write? V1 square by 2g, that is under root of V2 automatically 0. So P2 by rho g minus P1 by rho g, like this. Or V1 can be written as, V1 can also be written as V1 can also be written as 2g under root of P2 by rho g minus P1 by rho g. And here, whatever the things we are measuring velocity of the fluid, we are simply writing in terms of this will cancel out. So 2 by rho. This we are writing stagnation pressure minus static pressure. We can also write, we know that stagnation pressure will be equal to what? We know stagnation pressure is equal to static pressure plus dynamic pressure. So we can write V1, that is equal to 2 by rho, that is dynamic pressure, right? So that is also one way of calculating the V1, velocity of the fluid. Make a note of it. Once it is done, let me know. Dynamic pressure directly we used to write rho v square by 2. So for measuring the velocity of the fluid, you need the dynamic pressure, not the total pressure or static pressure. So we also write this to be total pressure. Once it is done, let me know. Once we will do the some numericals, things will be clarified regarding this pitot tube and pitot static tube. Done. So here we have some terms that we would like to take regarding the Bernoulli equation, that P plus rho v square by 2 plus rho gh. In this one, there is some specific terms are there that we must be familiar with that. What we are writing, P is a static pressure. It does not incorporate any dynamic effect. It represents the actual thermodynamic pressure. Rho v square by 2 is nothing but the dynamic pressure. It represents the pressure rise when the fluid is brought to the rest conditions isentropically. Rho g jet is nothing but the hydrostatic pressure term, which is not the pressure in real sense, since its particular value depends on the reference which is being selected, right? Generally, we say that is a fluid weight on the pressure. That whatever the potential energy we are writing, right? Potential energy, mgh. That is what they have told about, no, rho g jet, right? Now, so here, my dear friend, all of you have noted down. Done. I think this we already covered in Bernoulli. Done, guys. Here, this is what the formula which we have already written. P stagnation minus P static divided by rho. Now on the next particular instrument we have pitot static probe. In pitot static probe we have the two holes, not only single hole. We have the two holes which is being there in the pitot static probe. Now whatever the aeroplane speed is there, which is being measured by which instrument? Pitot tube or pitot static tube? Tell me guys, whatever the aeroplane speed which is being measured, there we have pitot static probe. Right here, why we have this particular tube? There is a reason for that. Now you understand there is a two holes which you can see very clearly. Let me mark it by red color. One hole is here, and many holes are there on the circumference of the tube. Now there is some specific purpose is there for placing the multiple holes circumferential of the tube. Now here you can see, right? Here you can see after putting the heading pitot static probe. You know that pitot probe is there where we have the hole at exactly in the front facing of the flow. The flow is happening like this. There only we place one hole. That is a one hole. That is for measuring. That hole is there for measurement of stagnation pressure, not for the static pressure. Now, whatever the surface hole is there, as you can see here, these surface holes are there for measuring the static pressure. My question is, why the front hole is not there for static pressure? Why only circumferential hole is there for the static pressure? Anybody know the reason for that? Just think and tell me. You might be thinking, sir, the whatever the front hole is there, why only it is giving me the values directly stagnation pressure? Yeah, that is correct only because in pitot tube also we have seen the front face of the tube which is being facing the flow. There is a hole, but here we have on the circumference also, and that circumference is not for the stagnation. That is there for the static. Why it is there for the static? Tell me guys. Because you try to observe whatever the flow is there, flow is happening like this. When the flow is happening like this, now tell me the liquid will be flowing inside the tube through the circumferential hole in this direction or not? Perpendicular to the flow directions. Actual flow direction is like this, and whatever the hole is there, let me consider this hole, the liquid is going perpendicular to the streamline or not? Initially perpendicular, whatever the parallel streamlines are there, that liquid is going perpendicular to that streamlines. Tell me guys, if that is going perpendicular to the streamlines, that is just like a what? Static fluids, because there is a no component. It is just flowing because there is a hole and it is being getting inside the tube like this. That is not flowing. That is just a static fluid inside the tube because there is a no component of velocity which is perpendicular to the streamline. So it is just like a static fluid only. And whatever the pressure we are measuring, that is a static fluid measurement. Getting my point, all of you? Tell me guys. Because this hole is facing exactly the flow velocity, right? Directly. So exactly directly it is being facing the flow velocity. That means what? We cannot, here we can again apply the static law because the fluid is coming to the rest condition. But outside of the tube at point number 1, we cannot apply these static conditions. We cannot directly write these static equations, right? Now my question is, suppose there is a tube like this. Now in this tube, tell me, in this particular tube, even though the point number 2 is inside, can we apply static law? Can we write P2 is equal to rho gy directly? Tell me guys, all of you. Hello, hello. My question is clear to all of you? Yes. Whether my question is clear? if I place the tube, which is not the pitot tube, it is just the tube which is being inserted in the pipeline. Tell me, guys. There is a no mouth opening of the tube is like this. This is my pitot tube, but this is not the pitot tube. Here the fluid is not coming to the rest conditions. The fluid will still flow. So we cannot directly write like this. This is not valid. All of you are understanding my point? Tell me, guys, whether things are getting clarified or not. In which condition we can apply the static law condition, in which we cannot apply. Please understand, because they are playing with this fundamental thing, right? If I show one question, whether you have tried or not, I don't know, but you please try that. I just left it for some good purpose only. After finishing the pitot static probe, you please try this question, which has been one of the beautiful question they can ever frame on the topic of because see, some of you might be thinking, so this is exactly what we have, the pitot tube, and directly straight away you will write the formula. They are asking the volume flow rate, so you will say area into velocity, and you will write a velocity will be under root of 2g, and this dynamic height, that is h2. So this, you might be thinking this will be the option, but that is not the options. Hello, 8 हाँ 8 8 8 बजे आऊँगा मैं करीबन. हाँ, बोल दीजिएगा उनको. Hello. All of you are understanding my point, what I'm saying. This is not the pitot tube. They are asking what is the volume flow rate through this tube. They are asking through this particular tube. They are not asking the volume flow rate through this particular pipe. Even they are asking for the pipe, that is not the answer. That is not the answer. So it is one of the good question. You try to find volume flow rate through the tube and volume flow rate through the pipe. Both the questions you try that and tell me the particular answer. Right now, we will not be doing that. We try it as a homework, right? It's a very simple fundamental of Bernoulli equation has been tested over here. But some of the students in a hurry, they will think that pitot tube, we know the formula, velocity formula, and directly they will put the option, right? But this is not the pitot tube. So I think that is clear that when we can apply this statics law, when we cannot apply. Now, so it is clear that all of you just tell me whether it is clear or not. Whatever the circumferential hole is there, that is not for the stagnation pressure measurement. That is only there for the static measurement. Yes or no? It is just like a piezometer tube. See, it is just a piezometer tube where the tube is there like this, and the flow is happening inside the tube perpendicular to the streamlines. It is also happening like this. Flow is like this, but flow in the tube is happening perpendicular. Is it not resembling the same situation? Tell me, guys. Yes or no? Whatever the function of piezometer is there, that function has been fulfilled by the circumferential hole right now. So there is no need to putting the extra instrument, extra cost that is we need to bear, right? So instead of that, all the functions has been fulfilled by single pitot static probe. Now again the question will be there, sir, how can we measure? By this we are measuring stagnation, by this we are measuring static. How we can take the difference to measure the dynamic pressure? Because we know that the dynamic pressure equal to P stagnation pressure minus P static pressure, right? So after revising also, suppose when the course of FM will be finished, no need to worry, I will be available on WhatsApp at any time, but I will be available maybe from next week onwards, right? So whatever your silly doubts are there, any doubt is there, you can just WhatsApp me. Your detail, all explanation I will give. I will try to give best possible explanation, whatever it may be possible, that I will try to give. So that, see, I cannot discuss each and every minute detailing in the class, right? Whatever it is possible, I'm trying to putting over here. But if at all anything getting left, that will be clarified, right? So here, how can I measure the stagnation and static differences? That for that we have the different instruments. For that we have different instruments. One is directly differential pressure transducer is there, right? You know that how the transducer is working, all of you? Any transducer, pressure transducer for pressure measurements? Piezoelectric transducer? We have piezoelectric, transducer. I will tell you the very basic simple principle behind that. Piezoelectric means there is a material, piezoelectric material, and which is being placed by two electrode is there, and this is being connected to some like this, some electrical circuit, right? So what will be there when we apply the pressure, right? When we just apply the pressure on this piezoelectric material, that whatever the pressure we are applying, that is directly proportional to EMF which is being getting generated. So with the help of whatever the reading is there, corresponding to that reading, we will see that how much of pressure difference is there. So that is our pressure measurement instruments, right? Piezoelectric we have, many other we have, right? Sometimes we use the dial gauge indicator also. Sometimes we use what? Burden tube also we use it. Getting my point or not? So anything you can use it, that you try to connect whatever the stagnation probe is there, a stagnation tube which is being coming, right? The red color one. See, the red color one which is there, it is being connected to one end of the transducer, and other end of the transducer is being connected to this pitot static, this static probe, and directly it will give me the reading of P stagnation minus P static, because P stagnation is what, more than P static. And you know that directly when we know the difference, let's say here this is what, this is P1, and let's say this is P2. Directly when we know the differences, we can able to measure the velocity. Make a note of it. Sometime, sometime we can also use the manometer also. I will tell you how this pitot static probe we can model it just like a single U2 manometer. I will show you. With the help of that also we can measure the free stream velocity. Try to read this no function of how the piezoelectric transducer is there. You just try to see the animation. That is a very good thing. When you keep observing a small thing, when you start learning. Hello, hello, I'm audible. I'm audible. Hello, hello. It's totally bad luck which is happening actually. I don't know why. There's a power. Actually, yes, huge raining happened here, in Chhattisgarh. So frequently it is coming going in all the cities. So I thought that everything was going fine when I observed in the afternoon and in evening time. Then I kept this particular timing. But again, suddenly, just now, it happened again. Hello? Yeah, yeah. So Monday, definitely we have to take. I have to take on Monday because from Tuesday onwards, I am actually I'll be busy for next 5 days. So hello, hello, I'm audible. Yes, we'll start in 1 minute. Hello guys, I'm audible. Okay, so we are discussing about this the concept of transducer, how it is working. So this is nothing but differential pressure transducer, or basically manometer to measure the P1 minus P2. Getting my point? I must say no, now it has to be visible, right? So here I was talking about the transducer, that is a pressure transducer, which is nothing but piezoelectric transducer, right? It is one of the transducer where we have the electrodes. In between the two electrodes, the electrodes are connected to the electrical circuit, and where the forces has been applied on the electrical this electrodes, and whatever the surface area is there, we can directly measure the pressure. And with the help of pressure, that pressure is nothing but what, EMF or voltage which has been generated in the electrical circuit, right? That is a one type of transducer. We have strain gauge pressure transducer. Whatever the pressure changes are there, that pressure changes we are directly measuring with the help of what? Resistance changes. That resistance changes we will be measuring with the help of what? Voltage, right? So we have different instruments. You just go through the YouTube videos regarding animation of any instrument, you will come to know. But here my question is that how we can measure by using the manometer, like this manometer. How we can convert our pitot static probe in the form of manometer, that is what we have to observe. Now, put a note. So here what I'm doing, I'm placing one. So there is a flow which is happening, u infinity, that is the free stream velocity. And here we have instrument called manometer, not manometer, but we will place it like a manometer, like this here. But we will try to bend this manometer tube, like I have drawn up to some height that is not correct, like this. So this is a pitot static probe. Let me consider the different points. So point number one here, point number two, just inside the, just inside the what we call uh, the tube, the pitot tube, and we do have the manometric fluid like this, manometric fluid. This is the manometric fluid. Now in this case, my different, we have the some height which I'm denoting over here, something like this. The difference of this height, I'm calling this to be x, and from this to this height, I'm calling from here to here as y, right? So point number one, just outside the tube. So we can, what we can have, we can have it like this. Imaginary extension, you can place it like this. There is a no tube which is being extended up to the point one. It is just an imaginary view of that, right? Now here my different, when the flow is happening like this, but your fluid is going like this. So that is my static pressure, right? You know that how the working principle of manometer is working. So we have to measure the pressure till here. Let me consider point number m, point number n. What we can do, we can have pressure at m, that is equal to pressure at n. Any doubt in this? By the manometric principle, can we say like this? Whatever the pressure is there at M point, and the same pressure will be there in the end point. Because when the 2 points lying on the same horizontal line, there will not be any difference of pressure. Right? Either you can take over here or you can take over here. But there is no need to take point number M dash and N dash because already the same fluids are there with the same heights. What is the pressure at point number M? Can we write the pressure at point number 1 will be, point number M will be, it is just like a tube only, right? One end of the tube, one end of the manometric tube. So it is something like this, where it is being connected to the 2 points. One is what? P1, other is P2. This point number 1 is measuring the static pressure. Point number 2 directly measuring the value of what? Stagnation pressure. Can we say like this? Because point number 2, it is inside the tube. Outside the tube. Point number 2, inside the tube. Inside the tube. So don't think that the point number 1 is also you have taken the inside. No, no. I have just extended it for your imagination purpose. Right? So now what is the pressure at point number M? So can we write P static plus what should be the value? Can we write here whatever the liquid is there, that is my rho gy up to this particular height, plus rho gy plus rho of manometric fluid g into x. Any doubt? Till here. Check it out. By the hydrostatic law, can we write like this? Can we write like this? By the hydrostatic law. Tell me guys. Yes. Can we write like this? Tell me guys. By the hydrostatic law, can we write like this? What we used to write? Pressure at this particular point from here to here, whatever the total height is there, that is what we used to write. Right? In the same manner, we are writing over here also. What is the pressure at point number N? We can write P stagnation, that is there in the pipe, that is there in the pipe, plus up to this whatever the liquid is there. Which liquid is there? Only we have one liquid, or what? Only we have one liquid, that is liquid which is flowing of density rho. The liquid which is flowing of density rho. So rho g y plus rho g x. This rho g y, this rho g y will cancel out. So what we can write? P stagnation minus P static, that is equal to rho m gx minus rho gx. Rho m gx minus rho gx. Further, what we can write, my dear friend? Can we write over like this, divided by rho g, divided by rho g? So what we can write? P stagnation minus P static by rho g, that is equal to x rho m by rho minus 1. After this, what you are understanding from this equation, my dear friend? What you are understanding? What you are understanding from here? Just by knowing the deflection, whatever the manometric deflection value is there, we can able to get, because you know this rho m, you know this rho, because what is this? Mercury. You know density of the mercury, you know density of the fluid which is being flowing. Directly with the help of only x reading, you can able to measure the difference of stagnation pressure and static pressure, or rather to say stagnation pressure head minus static head. Once you know this value, nobody can stop you to get the values of velocity. V infinity. What is that? Under root of? Under root of what? 2g P stagnation minus P static by rho g. This is what the formula we have, right? This is what the formula we have written. So further what we can write? Under root of 2g x rho m by rho minus 1. Please make a note of it. Once it is done, let me know. This is also called as differential head of the manometer. differential head of the pitot static tube, because we cannot directly call here manometer because it is not manometer. It is, we have bent it something like this. We are not placing like this. We have bent it. So now this is not a manometer. It is a pitot static probe. Pitot static tube. Is it clear, everyone? All of you understanding? Tell me, guys. Right? Because see, do not worry why we are writing like this. This is nothing but hydrostatic law. See how we are writing hydrostatic law. It's a very simple one, right? Uh, what we used to do in the downward direction, pressure is keep on increasing. So what we write, P static plus rho g, this rho, and this is nothing but rho m. Rho g into what? Up to what height it is there? It is there up to the height of y. Y plus rho m g into x. Just like what we have studied in the manometric principle, in the manometer. Same manometric equation we are applying. And why we are applying the static law over here? Because the fluid is flowing perpendicular to the streamline inside the tube. Inside the tube. And here why we are able to apply for the point number 2? Because point number 2 just become at the rest condition. So whatever the fluid is there, which is being there, it is not flowing. It is just there inside the tube. Right? The moment fluid will be start flowing, just like I shown one example, gate 2022, we cannot say, we cannot apply the hydrostatic law or whatever the static law which is there for the static fluid. Right? Now, once it is done, let me know, we can solve some examples. So there are many ways. Either you have transducer, one instrument which can directly give you the values of static and stagnation, directly take the difference and get the values of V infinity. Or you have some manometric kind of device where you can able to insert inside the tube, right, in which the fluid is flowing. So with the help of manometric deflection, when you insert it, definitely here more pressure is there, right? Then what will happen? Here there is a what? Less pressure is there. Here more pressure is there because stagnation pressure is higher. So liquid will push this one, and the manometric fluid will rise. Whatever the rise is there, that deflection you can see with your own eyes. X some mm, 20 mm, 30 mm. That value you can keep it for with this formula, and directly you can get the values of P stagnation minus P static by rho g. That directly you can put the values in V infinity formula. All of you have noted down? All of you have noted down? Can I move to the next one? Shall you solve the problem? Now, so this is the particular problem which has been asked in GATE 2014 AE. Now read that problem. A student can able to measure the free stream velocity, that is U infinity, of a low speed wind tunnel using a what? Using which particular instrument we can able to measure, they are asking. So we can able to measure that by pitot tube alone, aligned with the flow directions, right? I don't think it is possible. We can only get stagnation pressure. we can only get stagnation. We need static pressure also, so we cannot able to measure. Second point, pitot tube aligned with the flow direction with the static pressure measurement device at an appropriate position on the wind tunnel. That is also correct. Second statement is correct. Pitot tube aligned with the flow direction along with the barometer pressure reading of the outside ambient. So again, there is a no need to placing any place any barometer, because barometer will give you PATM pressure. We don't need here PATM. We need static pressure, right? That is also wrong. Pitot static tube aligned with the flow direction will give me the values of free stream velocity. So that is nothing but 2 and 4 is correct. So C option is correct. So make a note of it. Done, guys. Can I move to the next one? Can I move to the next question? No, I think it must be clear to all of you. All of you can read this one, or should I zoom it? Is it fine? The arrangement shown in the figure is nothing but measuring the velocity of a gas which is having a density. That means here density of the fluid. Density of the fluid is given as 1 kilogram per meter cube, which is flowing through a pipe. Acceleration due to gravity is 9.81. The manometric fluid is a water one, and manometric is what? That is water. What is the velocity? Velocity value they have given as 20 meter per second. They are asking differential head between the two arms of the manometer. This, for our case, this is x, right? So we know directly the formula, right? What is the formula we have? 2g x rho m by rho minus 1. So this is 20. Now anyone getting doubt? See, I will come to that doubt. What I'm asking. X is what? We have to calculate. And rho m is what? 1000 minus 1. So 20 square 9.62 into 999 into x. And if you just calculate what is the value, so you will be getting x value as 20.41 approximately as mm. Now my question is, now how many of you are getting the doubt? How many of you are getting the doubt in this particular question? Sir, it is not a pitot tube because it is not being there like this. Tell me, guys. Even though they have not given the mouth opening of this manometric, pitot tube, pitot static probe, even though it is not given, but we have to think about that because we are measuring the velocity, and how we can able to measure the velocity until unless we have this pitot static probe. Getting my point, all of you? If suppose you are directly placing one tube like this only, where we have the mouth opening not as we have discussed, but in some different manner. How can you measure the velocity? Tell me. You cannot able to measure the velocity, right? You have to measure the velocity. That means what? There has to be pitot-static probe. In the diagram, it is not given. In actual figure also, it was not given during that time. It doesn't mean that it is they are asking something else. Is that getting my point? All of you. Because see, they are mentioning the velocity is 20 meter per second. Of which one? Of the gas which is being flowing. All of your understanding. This equation itself you will not be getting when you have the mouth opening straight one, right? Like this. Understanding? Tell me, guys. Because if this small confusion you will not get clear, then what will happen? During the revision part, you will stuck, sir. You only said that fluid has to brought to rest condition, right? Isentropically. Definitely, then only we can able to measure the stagnation pressure. Otherwise, there is impossible that we can able to measure the stagnation pressure. We cannot able to measure stagnation pressure until unless we do have this mouth opening just like a narrow one, where the fluid is brought to the rest condition like this. Very small opening in such a way that fluid will say why there is a very small opening is there. It is just like a almost no opening. So velocity will be zero at that point, right? Now. So make a note of it. Once it is done, let me know. Now, some of you might have observed one more thing, sir. Whenever the liquid is flowing, whenever we have simple YouTube manometer, not an inverted one, we always place the manometric fluid of more density. Anyone know the reason for that? Why we can't have the density lesser than gas density? For example, if I ask you, why we are not placing the some other gas over here? Let's say this is a gas number 1. I can place gas number 2 of lesser density than gas number 1. Will there will be any particular problem in measurement of that? Yes, there will be problem when the liquid will exert some amount of pressure, right? Because you know that at the point number 2, which are there inside the tube, exerting more amount of pressure onto the free surface of the liquid. So here, if you are having the gas which are of the low density as compared to the gas which is flowing inside the tube, what will happen? It will try to deflect, right? It will apply huge amount of force, right? And due to that, what will happen? The gases will start fluctuating. We may not be able to take proper reading also. This H value we cannot able to take this proper reading also. It will keep on fluctuating because here also they will push, here also they will be getting pushed. So where exactly we have to calculate the value of H? That has to be some stable value, right? So for that purpose only, there will not be any fluctuation. To avoid the fluctuation, what we do, we always place the manometric fluid which is of higher density than the gas or maybe liquid which is flowing inside the tube. But when you do have this inverted U2 manometer, for example, in that case, my dear friend, always remember we have to place the manometric fluid which are of lesser density than the liquid or gases which is flowing inside the tube, inside this particular tube. Getting my point, all of you? All of your understanding? Tell me, guys. And why we are keeping the lesser density than the flowing fluid? So that this density, this manometric fluid will not exert the pressure. The reading fluctuation should not happen there, right? So that's the reason we are keeping the lesser density as compared to the fluid density which is flowing inside the tube, right? Now, moving on to the next question. Can you solve this question very quickly? Please try that. Now, so all of you are understanding or not? Tell me, guys. Yes, I'm not getting proper reply. What happened? Understanding this, these are the very simple devices, right? Do not do any mistake in exam. Very simple numerical will come. Try to attack the questions directly. The pitot tube of aircraft registered a pressure. Now, pitot tube. Now, pitot tube will measure which kind of pressure? They only mention that pitot tube, not pitot static tube. So directly it will give me the values of stagnation pressure. So I should directly write without any thinking. This is nothing but 54051 Newton per meter square. Directly it will give me the stagnation reading. Static pressure, density, ratio of specific heat of the free stream, they have given something like this. That means static pressure P infinity they have given 45565 Newton per meter square. The indicated air speed will be what? That's a very simple formula. 2 by rho P stagnation minus P static. Put the value, you can get the answer. Directly we got the formula, right? 2G P stagnation by rho G minus P static by rho G. Same formula, but this G cancel out and we have taken density outside. Rho is given as what? 0.6417 fluid density, right? Which is flowing. B is correct. B is correct. The stagnation pressure is what? 54051 minus 45565. Once it is done, let me know. So when you calculate, you will be getting the answer as meter per second. Done. Now try to solve this question. The low speed wind tunnel has the contraction area, something like this. And they have mentioned the static pressure difference between the settling chamber and the test section is 40 centimeter of water column. So now what you're understanding? The manometric fluid is 1000. The fluid which is flowing in a wind tunnel testing machine is nothing but 1.2 kilogram per meter cube. G value they have given. The test reading they have given at a particular section 40 centimeter. Directly the reading of X is given 0.4 meter. What else we have to calculate? We have to calculate the speed of the air in the test section. That's a very simple formula. Under root of 2G X rho m by rho minus 1. X is what? 0.4 thousand. So when you calculate, you will be getting 88.545 meter per second. 80.8. Now let me calculate. 80.82, correct. 80.82. That is correct. This is point 4. So these are the what redundant datas that is of no use. They have just given the configurations of wind tunnel testing, contraction ratio, and cross sectional area of the test sections. Now this question you try as a homework and tell me the answer. One of the good question. Aircraft is cruising at an altitude of 9 km. The free stream static pressure density at that altitude is given like this. The pitot tube mounted on the wings directly measures the pressure of what? Stagnation. The cruising speed they are asking. So once again, very easy question. But some twist is there because of some altitude height. That you need to take care of that. Getting my point, all of you. Can I move to the next one? No, guys, the next chapter, the laminar flow. First, we will discuss about the internal flows. Then we will discuss about the external flows. Yes. Yes, we can proceed. Now, note down the laminar flow through pipe. That is the next chapter. The first flow we are discussing here is laminar flow, and then we will discuss something about turbulent flow. What is some special characteristic about the laminar flow and turbulent flow? What do you mean by the laminar flow? What do you guys mean by the laminar flow? Laminar flows is highly characterized by the smooth lines which are parallel with each other, right? Highly ordered motion like this, layer by layer motion. Whatever the liquid particles are there, right? They will not basically what interact with each other during the course of motion. But it is you can see very clearly, right? A dye which is being injected in the pipe, right? And if this V infinity, V average is not that high, in that case, what will happen? This dye which is coming out will be just like a laminar. Each and every fluid layer will be parallel to each other, right? Streamlines will be parallel to each other. Here, what is happening? Turbulent flow, which is basically highly specified by some velocity fluctuation and highly disordered motion. You can see whatever the liquid is there, one layer of the fluid, suddenly they will be start colliding with other layers of the fluids, right? Highly momentum transfer will happen in the turbulent flow. Due to that reason also, what happened here, you are not only having the see in laminar flow, we know that whenever the fluid is flowing in a pipe, definitely some kind of shear stress will be there, which is being offered by the wall onto the fluid, which is being offered by the wall onto the fluid. That is wall shear stress, right? That is the shear stress. But generally here in the turbulent flow, you are not only having the shear stress, you will be having two stress. Shear stress plus ED stress. Now, from where the ED is coming? Tell me, guys. From where this particular ED uh, shear stress is coming? That is coming because of what? ED viscosity. And why ED viscosity is coming? Try to think. If you know something basic about the turbulent flow, let me know, guys. Tell me, guys. All of you are understanding my question or not? What I'm asking. Why there is a ED viscosity is coming? Don't think that that ED, what we have discussed, wake region and all. Here, why the ED viscosity we are considering in the turbulent flow? That is my question. We also sometimes call this is nothing but turbulent viscosity, a turbulent stress. Why we are calling over here, right? Why there is a need of saying that here one additional shear stress? Generally, what is happening due to the interaction between the fluid particles? Due to the interaction between the fluid particles, huge amount of mixing is there. Huge amount of mixing and momentum transfer is there between the fluid layer. Some fluid layer which are moving at a very low speed, they will be start sending the message to the other fluid layer. Those who are moving with some higher velocity, that there is a lot of restrictions has been imposed by the ball onto us. So how can you move forward with such a high speed? Huge amount of momentum message will be propagated. That message is also being propagated in the laminar flow, but that message is very less. But in the turbulent flow, directly they are interacting and directly they are shaking the hands with the fluid particles, and they are saying that whatever the wall is there, they have been rested us. Some of the particle which has been struck on the wall, which they got at the what rest condition, they cannot move forward. That message will propagate very quickly in the flow called turbulent flow. Due to that, additional shear stress between the layer of the fluid happens. Because of remixing, some additional shear stress between the fluid layers occur. That is nothing but turbulent shear stress. Getting my point? All of it. So different scientists or researchers have been given the semi-empirical theories about this ED viscosity or ED shear stress. Just like what we used to write shear stress, something like mu into du by dy. But here we used to write ED viscosity as ED shear stress as mu t du by dy, where mu t is nothing but ED viscosity. This is nothing but viscosity, just a fluid property. This is nothing but flow property, not a fluid property. ED viscosity is coming because of the huge amount of intermixing or fluctuation which are happening in the turbulent flow. So in turbulent flow, whatever the velocity component is there of single fluid particle or whatever the fluid particles are there, they have two components. One is average, second is fluctuating component. But in the laminar, you have only one component, that is U bar. That's it. The velocity with which the fluid is flowing in a pipe, that is the average velocity. But here, not only they have the one component, they will be dancing, right? They have one component and they will be start dancing like this. So this is nothing but fluctuating component. This is nothing but average component. Both the components are together constitute the total velocity in the turbulent flow. So don't think that in turbulent flow some wake region is forming because of wake region. ED formation is there, and that we are calling ED viscosity or ED shear stress. Not like that, right? Here the meaning of ED shear stress or turbulent shear stress, it is just denoting the fluctuating component, right? We also represent this one. Make a note of it. Just wait. So here you can note down, put a note, very important note. We also write the turbulent shear stress. This is nothing but turbulent shear stress. We also write turbulence shear stress between the fluid layers will be given as tau t, that is rho into u bar v bar u dash v dash bar. We also call this to be Reynolds stress. We also call this to be a Reynolds stress.